step back from that ledge, my friend. We could cut ties with all the lies that you've been living in. And if you do not want to see me again, I would understand. I would understand. I would understand. Hello everybody, welcome to this week's edition of Video Notes for Mr. Flugum's AP Chemistry class. That's right folks, this is for AP Chem. And we are going to be introducing our next unit, which will be equilibrium. Alright, and we're going to be talking about what is equilibrium in chemical reactions. So here we go, let's get started. So the first thing I want to do with you guys is this. I want to review molarity. Okay, so calculating concentration. When we talk about calculating concentration, that means how much stuff is in how much volume, right? So concentration of solutions in chemistry is measured in molarity. So molarity, you guys, right, is, remember this, right? Molarity, that's the big M, capital M, is equal to moles per liter. Okay, so moles divided by liters gives you molarity. Now once we've got down molarity, we need to start talking about this, right? What happens with chemical reactions? Well, some reactions go to completion. For example, when you take HCl and it is dissolved in water, it forms H plus and Cl minus ions. And it is all the way towards the right side there, towards the products, okay? So in that case, we use a one-way arrow. On the other hand, we have reactions that are reversible. Okay? For example, right, water, when it evaporates or condenses, it goes one direction or the other, depending on conditions, right? Pressure and temperature. And at the same time, we have the dissolving and precipitating salt, right? It goes one way or the other, depending on temperatures and conditions. However, here's the deal. Most reactions that we carry out do not go to completion. All right, that means they don't go all the way one way or all the way the other. And this is what's called dynamic equilibrium. And that's what we're going to be focusing on a lot during this unit. Okay? Now when we have these reactions, we have this two-way arrow here, right? Which shows that the reaction is going in both directions. That's because we've got equilibrium. So what does equilibrium mean? So to explain equilibrium, I want you to check out this graph here. And this graph represents data from this reaction up here, which is the decomposition of nitrogen, dinitrogen tetraoxide into nitrogen dioxide, right? If you notice, we start right here at the beginning of the reaction with all of the N2O4, right? And zero, right? 0 moles of NO2. Now as the reaction proceeds, you notice the N2O4 decreases and the NO2 increases. Eventually what happens is we reach what's called equilibrium right around about here. Okay? This is where we reach our equilibrium. Okay? There's our equilibrium. If you notice what happens from that point on, the concentrations of both NO2 and N2O4 remain the same, no matter how long the time goes on. So what's happening in this reaction? What is causing this equilibrium? Well, here's a second graph to kind of explain what's going on, right? If you notice here, we've changed our y-axis to the rate of reaction, right? What happens is this, right? The rate of reaction as we go, the rate of production, I guess you could say, of N2O4 levels out. And the same with NO2. It also levels out as well, okay? Until we reach rates of reaction being the same. So that means this. The reaction going this way, right, happens at the same rate as the reaction going this way. And that is what maintains equilibrium and maintains those constant concentrations. Okay, so what does all this mean? It means this, right? Basically, the forward and reverse reactions occur at the same time. So we've got one reaction going in one direction and one reaction going the other, right? The reverse of it, okay? And what happens is this, right? The rates of those reactions, forward and reverse, are the same. Okay, that's the last graph that we looked at, right? So because those rates are the same, right, the concentrations within the system of the reaction remain the same. Now, in order for all of this stuff to happen, it needs to take place in a closed system. So over here is a closed system, right? Okay, if you notice we have the stopper on the bottle, nothing can escape or come in. Now, if things were able to, if we had an open system, which would be the opposite of that, if we took that cork off, that would be an open system. All of a sudden now, things could leave or come in, which would change concentrations and therefore would change our equilibrium. Okay, so we're going to look at a few things during this unit. One is what happens when we reach equilibrium, right? And how do we calculate that? And also this, right? How can we mess with equilibrium? Okay, what can we do to a system to manipulate it in order to get what we want? Well, thanks for tuning in, you guys. Those are the basics of equilibrium. What we're going to do on Wednesday is we're going to start looking into, okay, how do we start calculating this and using quantities in order to measure and investigate equilibrium. Thanks for tuning in, you guys, and I'll see you in class.